Hello. So in this video, we're going to look at Haberman's section chapter 2.5. And so kind of the goals of this chapter twofold. First, we're going to solve Laplace's equation on a rectangle. Recall that kind of this condition, nabla squared u is equal to 0. This arises if you ask about equilibrium or steady state solutions to the heat equation with some prescribed boundary conditions. But we're going to see how kind of the techniques that we've been developing over the past few weeks all come together to give us a way to write out explicitly what solutions to this equation look like. Okay. And so then related, we're also going to look at solving the same equation, nabla squared u is equal to 0, on a disk, which corresponds to finding the equilibrium temperature, right, for the heat equation in polar coordinates. Okay. And then kind of the third piece after all of this will be some more qualitative aspects of each of these equations. But yeah. Okay, so for the first part, what we're going to do is solve, right, heat equation on a rectangle. And so the geometry that we're going to work with is the following. So kind of the x-axis, y-axis, we're going to work between x equals 0 up to x equals L, as well as y equals 0 up to y equals h. Okay, so our rectangle has a length and a height. This coordinate is x, this coordinate is y. And so what we're interested in is the following PDE, right? Nabla squared u is equal to 0, along with the boundary conditions where kind of we're imposing the value of u, right, at each of the kind of boundary segments. Okay, so for example, u of 0 comma y is equal to g1 of y. This is saying that at x coordinate 0, okay, so that's at x coordinate 0, for any y that you plug in, right, the solution has to be equal to this given function. And so the given function, we might graph like that. So this would be g1, okay? And so then, yeah, so this would be an illustration of at least this boundary condition. Another boundary condition, u of L comma y is equal to g2. Well, plug in x equals L, we're looking at this line right here. We're saying the value of our solution on this line is this given function g2. And so g2 we might sketch as some function like that, right? Similarly, right, u of x comma 0, y is equal to 0. So we're looking at this line right here. And we're saying whatever our solution is, yeah, has to have some profile that's given. Okay. But so this is the problem that we're trying to solve now using separation of variables and some of the other techniques that we've developed. So one thing to notice is that, right, as written, this is not a homogeneous kind of boundary value problem, right? Because kind of these boundary conditions are not equal to 0. Right? If you have one solution in U and if you have another solution in V that also satisfies all of these boundary conditions, and then you consider the function U plus V, right? Well, nabla squared of U plus V is going to be 0 because U and V both satisfy this. But now, say, for example, U plus V evaluated at 0 comma y, okay? This is going to be equal to 2g1 of y. For example, okay. So the sum of solutions will not be a solution, right? Because we're working with non-homogeneous boundary conditions. So technically, we can't use the principle of superposition, some of the other techniques we've worked with. But it turns out what we can do is break up this problem in a way that we can use some of these homogeneous techniques, like the principle of superposition. Okay? And so that's going to be illustrated here. So go ahead and scroll down. So this is the same rectangle from above. Okay. This would be kind of G1, G2. This is F1 right here, and then F2 right there. Okay. And so what we're going to do is, instead of solving kind of this problem as given, where we're actively trying to match all the boundary conditions at once, what we're going to do is actually solve 4 different problems. Okay, and so these problems are, so for example, this one right here, what we're going to do is we're going to say, well, for y equals h, so right here, we want u of x comma h to equal f2 of x. And then the value of u on every other segment is going to be 0. Okay. So now what we get is an almost homogeneous boundary value problem where there's only one piece that's not homogeneous, right? And that's this piece up here. But kind of this piece and this piece, those are 0, right? The value of u has to be 0 there. So it's homogeneous. This piece down here is also homogeneous, but we're going to use separation of variables. So kind of this piece is going to be matched with this piece right here. But the idea here is that, right, we're going to break up solving kind of the thing that we really care about into solving these 4 smaller problems with 3 out of the 4 boundary values equal to 0. And then we're going to sum up the solutions. Okay. Right. So, for example, what we're going to do is we're going to solve this one where we say u is going to be g1 of y at the kind of left boundary segment, but then u is going to be 0 everywhere else. Okay. So going back up to the picture, so g1 of y is non-zero, and so that corresponds to, this is the problem that we're going to solve. We want Nablus squared of u3 is equal to 0, and u3 of 0 comma y is equal to g1 of y. Okay. So we're going to go through the work to solve this problem. In practice, you could do the same exact procedure to solve this problem, and this problem. Okay. So that's going to get you 4 different solutions. All of them satisfy Nablus squared u is equal to 0 on the interior. Okay. But each of these are going to have one non-zero boundary condition, all the rest 0 boundary conditions. Okay. But then if we add all of these up, right? So for example, u1, u2, and u4, they will have 0 boundary condition for here. Okay. So when we add up all 4 of these functions, the only contribution we're going to get is from u sub 3, because u1, u2, and u4, right, for these values are all equal to 0. Okay. And so in that way, we're recovering our original boundary conditions. So written out, so what we're going to do is we're going to solve these 4 different problems and then add them together, and that'll be the solution to the original problem. Okay. And so in kind of these notes, we're not actually going to work through all 4 of them. We're just going to work through one of them. But again, the procedures are the same for all 4. Okay. So we're going to use separation of variables. We're going to separate our desired function into a piece that just depends on x and a piece that just depends on y. Okay. And so the boundary conditions that we're going to work with, or at least the homogeneous boundary conditions that we have, are, well, h of L is equal to 0. And again, this comes from this condition right here, right? Because u sub 3 is equal to h of x phi of y. And what we're doing is we're saying we're plugging in x equals L. So this is h of L phi of y. Okay. And so a similar reasoning, as we've done plenty of times, says, well, if this is 0, then phi of y cannot be 0 for all y, because then it's a trivial solution. So that forces h of L to be 0. Okay. So that's where this comes from. These other two boundary conditions for 0 and h force phi of 0 to be 0 and phi of h to be 0, the x boundary conditions. No, the y boundary conditions. But anyways, these are 0. Okay. So plugging the separated solution into the PDE, what does that give us? Well, take two derivatives in h and phi. So going back up, right? This is the PDE we're working with. This is equal to 0. Take the two derivatives, reorganize. We're going to end up with this equality. Okay. And so as before, what we're going to do is we're going to set this to a constant. Okay, that separation constant. But now we have a choice of sign for the constant. Okay. So one thing to notice is that, right, both of these look awfully similar to, well, I mean, both of these are essentially the form d squared psi over dx squared is equal to lambda psi. But now the question is, do we want to have lambda or minus lambda? Okay. So the observation is, well, for phi, right, kind of the y function, we have these 0 boundary conditions. Okay. And so we've worked plenty with, right, this piece right here and these boundary conditions, right? Together, these force the form of the solution phi to be a sine function, as well as forcing lambda to be n pi over L, or in this case, n pi over h, quantity squared. So what we're going to do is we're going to choose our constant so that we get oscillation in y. We really force that out. Okay. And so to get that to happen, here we're going to choose lambda with a positive sign. Right. Okay, and so again, the reason is, well, if we choose lambda with a positive sign, we end up with the ODEs. So this is what it looks like for h, right, the function of x, for which we only have one boundary condition. But what I was getting at above was, well, for phi, right, if we choose lambda positive here, how we've written it, the minus sign is with kind of phi, so that this is the resulting ODE. And this is one that we've worked with plenty before with exactly these boundary conditions. Okay. And so hopefully you recognize that, well, the resulting solution function is going to be sine of n pi over h quantity times y with the corresponding eigenvalue lambda. Okay. So because we want this solution or this form, that's why we chose the sign of lambda here. If you were to put a minus lambda, or if you were to kind of move this minus and write it right there, all of that's totally fine. We just chose this convention so that we could recognize relatively quickly this ODE, which gives us these solutions. Okay. But half of our work is now done, right? So we figured out what phi looks like from our product solution. Now we need to solve for h. And in particular, we know exactly what this lambda is for h. Okay. So yeah, so as I said, so plugging in what we've computed lambda to be kind of in there, the h ODE, this is what we're left with kind of one boundary condition. I mean, technically there are two, but we'll bring in the fact that right, u of x comma y is equal to g1 of y. We'll bring that in here in a little bit. Okay, so this is the ODE that we're now left to solve. So however you want to go about it is fine. The technique I have written kind of goes from scratch, but what we get is, well, the characteristic polynomial for this ODE, right? If we're looking for solutions of the form, I call it h of x is e to the rx, right? If we're looking for solutions of this form, here's a condition on that constant r, which results in r has to be plus or minus n pi over h. Okay. So then in general, the solutions are going to be a linear combination of the piece where r is positive, right, so right here, together with the piece where r is negative, so right there. Okay. So we have one kind of prescribed or homogeneous boundary condition, that's h of L is equal to 0. So plugging that in, what do we get? Well, 0, so h of L is equal to 0, so 0 right there. Plug in the L to the x's, we get this expression. Okay. And so multiply through by e to the n pi over h times L. That's going to get rid of this or cancel out with this term right here. So we end up with that, which tells us that, well, C2 is going to be minus C1 times e to the 2 pi or 2 n pi over h times L. Okay. And so if we plug that condition for C back into kind of the above, right? So move, right, this C2, so plug in for that. What we're going to end up with is this expression here, right? So h of x is some arbitrary constant to be determined, right? In this case, determined by our boundary conditions or our other boundary condition, but some constant times this combination of exponential pieces. Okay. Which, sure, we can work with this, it's not terrible, but the question is, can we get a slightly nicer way of writing out this expression? And so in this case, we have a cleaner way, we might call it cleaner, but if we use the functions sinh and cosh, where sinh is this linear combination of exponentials, cosh is going to be this linear combination of exponentials. Okay. What we get is the following. So notice that, so what we're going to do is we're going to say, well, what is this quantity right here? Sinh of n pi h times x minus L. That's going to give us, so if we plug in kind of the definition of sinh, we're going to get these exponentials. Okay. Distribute this n pi over h kind of in both places. We're going to end up with all of this. Okay. And so now what we're going to do, I believe, is factor out, we're going to factor out this e to the n pi over h times L. So this factor here, we see right here, right? So we're pulling this factor out. The question is, what happens over here? Okay. Well, turns out you're going to pick up another factor that looks like this. Another way to check is, well, take this, distribute it. Okay. Do we end up with this expression? In this case, yes, we do. Okay. So if you factor out this e to the minus n pi over h L, this is the resulting expression that you end up with. And yeah, from this, we recognize, well, this is just going to be some constant right here, right? So technically it depends on n, but this is just some real number. Okay. And then this is going to be some other function of x. And so compare that to what we had before, where we said, well, our solution h of x is going to be some constant times this function right here. So yeah, up to a constant, what we get is that h of x is essentially, right, sinh of n pi over h x minus l. Which you get by comparing, right? So you get by comparing this expression to this expression, which is equal to sinh of n pi over h times x minus l. So that's one way to see that h of x is equal to that. Another way would be to kind of go directly and say, where's the ODE? Another way to get this might be to say, well, instead of working with this basis of exponentials, instead, you can argue that, well, h of x is going to be c1 of sinh n pi over h times x plus c2 times cosh of n pi over h times x. Okay. This doesn't account for kind of this extra minus n pi l over h, but it's going to get you closer to expressing things in terms of sinh and cosh from the start. Okay. In the end, it's just another function. It's just another solution, right? It's just the form that the solution takes. So however you want to write it is fine. It's just some ways might be a little more interpretable or easier to parse than others. Okay. So this is a piece of our product solution for x. Okay. So bringing them together, right? Well, we said our product solution was going to be some constant times a piece that depends on y times a piece that depends on x. So plugging in, we get this expression, right? U3, so the solution that we care about, is some constant times sine of n pi over h times y times sinh of n pi over h times x minus l. Is the expression that we're gonna work with. So this is just one of the pieces, right? It depends on n. And so if we say, well, let's incorporate, why choose one n? Let's incorporate all of them. So if we sum over all possible n, we're going to get an expression of this form, right? Where now we've replaced these constants c with these constants a sub n, emphasizing their dependence on n. So this is the general solution for this OD or this PDE up here. Okay. It's going to be a linear combination of sines and sinh, but what we have yet to do is incorporate this other boundary condition. Okay. And so it turns out that this will be enough information to specify what those constants a sub n are. Okay. So let's see how that goes. Okay, so now what we're asking is, what are these a sub n? Well, we want our general solution evaluated at x equals 0. So plug in x equals 0 right here. We want our general solution to be equal to g sub 1 of y, x equals 0. Okay. So if you plug in x equals 0 up to into the above expression, we get, right, this thing with kind of a 0 minus L right there is equal to G1 of Y. Okay. So now here, notice that for each n, okay, this is a constant, this is a constant, okay, and now this is a function of Y. Okay, but we have some constant times a function of Y, sum them all up is equal to G1 of Y, right? These are just Fourier series, right? Same kind of series that we've seen before. So the question is, well, how do we get these coefficients a sub n? Same way we've done it before. Multiply each side, so multiply this side and that side by sine of m pi over h times y. Integrate from 0 to L to isolate the coefficients that we want, and then solve for a sub n. In this case, a sub m. Okay. So what does that look like? Well, so here I've done a few steps, so I can write it up here. So actually, let me, yeah, so it's going on here. So multiply this side by sine of m pi over h, sine of m pi over h y. Multiply this side by sine of m pi over h y. Okay. Integrate both sides with respect to x from 0 to L, 0 to L. Okay. The only piece that's going to survive on the left is when n is equal to m. Yep. Okay. So that's going to isolate this coefficient for m, but then we're going to have, right, what are the other pieces? Well, we're going to end up with a sub m times the integral from 0 to L of sine squared of m pi over hy dy times sinh of m pi over h times minus L. Okay. And so that's what's written right here. You integrate the other side, you're just going to get the integral from 0 to L of sine of m pi over h times y times g1 of y. Constant, constant, mystery constant. So taking all of this, moving it down there, we end up with this expression for these coefficients a sub m. Okay. So we know what these coefficients are. Okay, we've figured out these coefficients in such a way so that our solution u sub 3, so our solution u sub 3, plug in x equals 0, you get g1 of y. We now know how to figure out a sub n so that exactly this holds. This solves the PDE everywhere else, and we're done. Okay. So that gives us this u sub 3. Same exact procedure works to get u1, u2, and u4. Okay. So once you have u1, u2, u3, u4, add them all up, sum them up, or well, yeah, add them all up. That's going to solve the PDE. That's going to solve these non-homogeneous boundary conditions, and then you solved Laplace's problem on a rectangle. Okay, and so if we want to do the same thing for circles or in polar coordinates, similar strategy. It was just some slightly different pieces are going to come into play, but it's more or less the same strategy. So we'll see that next.